Our next topic is equilibrium calculations. The idea here is, again, the whole point of this exam is to determine what the final concentrations of our reactants and products are going to be when we reach equilibrium. That's going to be incredibly important in any of the applications of chemistry. Are we going to have a high concentration of some toxic byproduct or of some wastewater pollutant, or maybe the desired pharmaceutical product we're trying to make? The type of examples that we'll look at most are acid-base reactions, but now we have the essentials of equilibrium. We're ready to actually do the calculations to figure out how much stuff is present at equilibrium. This builds on our content from last class where we were looking at writing down the reaction quotient Q. We'll still need to do that. Last class we looked at, okay, based on the value of Q, we can say, is this reaction going to proceed left towards reactants, or if my Q was small here, I'll get larger to proceed right towards products. Now we'll actually be able to figure out the exact equilibrium concentrations of all of our reactants and products. One sort of nicety before we continue is this idea of Kc versus Kp. So in our last class, we looked at this Kc definition where we write things with a concentration bracket. Remember, anything in those brackets is a concentration in units of molar, or moles of HI divided by total liters of the container, or if we were in water, liters of the solution. We can equivalently for gases, since for gases the concentration is proportional to the partial pressure, we can write things in terms of the partial pressure of each gas. So P sub HI means the partial pressure of the gas HI. Remember, according to the ideal gas law, it's not something you're going to have to apply or use too much, but remember that we do have the ideal gas law, PV is equal to nRT, and moreover, if I have a particular gas X, the partial pressure of gas X is equal to, the partial pressure of the gas Px times the volume is equal to the moles of that gas N sub X times RT. So the concentration and partial pressures are always proportional. A bigger concentration is a bigger partial pressure. So for our purposes, we do have this relationship that describes between a Kp with pressure units and a Kc in concentration units. Basically, all you have to do is use the appropriate one based on which you're given. So if you're given a Kc, do everything in concentration units. If you're given a Kp, do everything in partial pressure units. Okay, so here is our first example. In this case, we're going to look at, this is a way to introduce what's called an ICE table, initial change equilibrium. So let's look at our graph on the left here. The experimental data, we have some N2 and H2 placed into a container, and we're able to track the progress of the reaction by looking at the amount of NH3 formed in molar over time. So we start at 0 and gradually form a certain amount of NH3. Our goal in this problem is to calculate K given this information. Before we do any of the math, I guess the first conceptual point is, what information did this give us? What do we know about equilibrium from the given information? If you look at the graph carefully, you should see that eventually what we're seeing is the concentrations level out. So if we look here, at some point here, this is at 2.62 molar, the concentration of NH3 is leveled out. And so out here is basically where our reaction has reached equilibrium out at this point. We started, not at equilibrium, and we did eventually reach equilibrium here. Now to calculate K, what we're going to do is go through the steps that we're going to need to apply to any equilibrium problem. So first, write the balanced equation and the equilibrium constant expression. The balanced equation, in this case, it's N2 gas reacts with H2 gas to make NH3. Now, again, we have to balance it. You can take a second to try to do that. In this case, the coefficients here, if I put a 2 on NH3, that balances the nitrogens. I now have 6 hydrogen atoms on the right, so I need a coefficient of 3 on H2 to balance the hydrogen atoms. So that is my balanced equation. A lot of times you'll be given the balanced equation, but definitely throughout this part of the class, there'll be times when you're not given it and you have to provide it yourself. For the equilibrium constant expression, this is that K is equal to Q expression. So now that we have the balanced equation, we can write that expression. The equilibrium constant K is equal to our products, NH3 squared divided by N2, has a coefficient of 1, so the power is 1, and then H2 cubed. So those are, again, the first two things we're always going to need to do when we're solving one of these equilibrium problems. Based on that, we now know that if I can figure out the NH3 concentration at equilibrium, which I know the NH3 concentration at equilibrium is 2.62 molar, I'll be able to plug that in, but I'm also going to need to figure out the concentration of N2 and the concentration of H2 at equilibrium. I can do that by calculating, right? I've got a certain number of moles. I could calculate the moles of NH3. So this is all just sort of a stoichiometry calculation, like an excess reagent, limiting reagent type question. But since we do this so often, we have a specific way to do these calculations. The method that we use to do these calculations, where we're going to compare the moles of, molarities of reactants and products, is this ICE table. So the first thing that we're going to do when we write down an ICE table is we start from the balanced reaction. So we have our balanced reaction, and then below it we write three different rows. An I row, which stands for initial, a C row, which stands for change, and an E row, which stands for equilibrium. Generally, we just abbreviate those ICE, and these are each rows in our table, and then each entry in our table is for each of the different substances. So I've got this table that will eventually have, 9 total entries in it. The first thing we need to do is convert everything to the proper unit. So because we're in concentration units, because our K equals Q expression looks like this, we're going to need to be in units of molarity. So that's the first thing we're going to do. Sometimes we'll write that here, write the unit here for the table is like moles per liter. So let's do that calculation first. The initial amounts of each thing, NH3 we started with 0, but the other twos were given the moles and the liters, so we can calculate that. The N2 initial is equal to, what do I have to do? I just need to take the moles of N2 divided by the liters of N2, or the liters of the, let's say, container. If it was a solution, we would call that liters of solution. In this case, then, that's 6 moles divided by 2 liters is equal to 3 molar. The same thing for H2, 8 moles of H2 in a 2-liter container, so that's going to be 8 moles divided by 2 liters is 4 molar. That was your initial concentration of H2. Now we can fill in the known concentrations, so we know the initial row. We also have some important information here. We could fill that in now or a little bit later. Depends on how you're doing it. Note that we do know this number down here. We know the equilibrium NH3. EQ is equal to 2.62 molar. That given information that is in this graph. Next, though, let's do the change row. The change row is always defined using X. Usually, how this is going to work is that we'll define it as minus a certain number of X's for reactants and plus a certain number of X's for the products. That's because in this case, if we look at our initial Q, it's 0 divided by 3 by 4 cubed, which is just 0. So we started with Q is equal to 0, and if we think back to our number line, if Q starts at 0, we're going to have to run this reaction to the right, forming products. That's what we observed here. We formed a certain amount of products, and the reaction did proceed to the right. It's not a bad idea to always do this comparison and check the value of Q, compare it to K to see what direction the reaction is going to proceed. But in this case, this reaction is going to proceed to the right. So when we define the change row, what we're going to do is do sort of plus X of the products and minus X of the reactants. And we use the stoichiometric coefficients there. So in this case, for N2, it's a reactant, so it's going to be minus X, and its coefficient is 1, so it's just minus 1X. For H2, though, it's a reactant, so it's going to be minus, but if I look at it, it has a coefficient of 3. So that means when I go to define the change row here, I'm going to define it as minus 3X. I always just use whatever the coefficient is. So my coefficient is 3, so my change gets a 3. It's a minus again because it's also a reactant. Now for the products, this is now going to be plus 2X again, where the 2 is to match the NH3, so plus 2X. Now at equilibrium, I can go in and write initial plus change is equal to equilibrium. So that's always the case here, is that these two things add together to get the final value. So I plus C is equal to E. So my equilibrium for N2 is 3 minus X. My equilibrium for H2 is 4 minus 3X. My equilibrium for NH3 is 2X. Now, at this point, I can use the table to determine X, K, any of my unknown concentrations. That's where this given information is really useful. From this row of the table, I now know that NH3 at equilibrium is equal to 2.62 molar, but it's also equal to, according to this entry in the table, 2X. So I can divide both sides by 2 and get X is equal to 1.31. The units are molar, which is always, again, in this case, we're in units of molar, moles per liter. Now at this point, I can calculate the other equilibrium concentrations. Because I know the value of X, for N2, the equilibrium N2 is 3 minus X. So I can do 3 minus X is equal to, and I know X is 1.31, so when I plug that in, I get 1.69 molar. H2 is 4 minus 3X. So when I plug in X equals 1.31, I get 0.4 minus 3X ends up being 0.07 molar. Now that I know all the equilibrium concentrations, now I can go back in and calculate K. So that was the goal. If I know all the equilibrium concentrations, I plug in and solve for K, or I calculate K. So at equilibrium, K is equal to Q, which is equal to, again, I have my formula up there, NH3 squared, so that's 2.62 squared divided by N2, just gets the power of 1, so 1.69, times H2 gets a power of 3, so 0.07 cubed. Okay, so here's the solution, 11,800. Just to show the left-hand side calculations, you can use that store button on your calculator to store a value to X, which could be convenient for these problems. Then for the second one, again, you should either use those parentheses around the denominator. So you'll either need, open parenthesis, type all the denominator stuff, close parenthesis, or use this, sort of more mathematical style division operator, where it forces all that stuff in the denominator properly, and you can just type it more the way you write it. Either one to force, make sure both of those terms are in the denominator. Again, if you have calculator questions, please just let me know. So our final answer, K is equal to 11,800. That gives us some information about this reaction. That's a pretty big number. This is a reaction that definitely favors products significantly. We can also see that in the fact that we've really almost completely run out of reactants. We still have a little bit of N2 left, but we've used almost all of our H2 here. and converted almost all of it into NH3. So a larger value of K, the further the reaction goes towards products. In this case, H2 is going to be more expensive, a little bit harder to work with and obtain, so it maybe makes sense to use a little bit more nitrogen to force the reaction towards products and use up the expensive H2. Okay, here's our next example problem, so take a minute to see if you can do this one on your own, writing out your ice table, calculating K from all the given information. Okay, so here's the solution. In this case, we're given the reaction, so nothing to do there, but the equilibrium constant expression, we should do that. So that's Q is equal to SO2 squared times O2 over SO3 squared because of the coefficients. Remember, something that people will do is they'll use the coefficients either too much or too little. SO2 has a coefficient of 2 and SO3 has a coefficient of 2. So the places we're going to use those coefficients are when we're defining Q and also in the change row. So in this case, we're going to expect to see like a minus 2x and plus 2x there because of the coefficients. We don't use the coefficients any other place, only in the change row of the ice table and in defining the value of Q, or the value of the equilibrium expression. Now we've written out our ice table, and it's time to start doing that. So we have our reaction. We know that we need to convert to concentration, so moles per liter, just like we did before. So SO3 initial is going to be equal to 12.0 moles divided by 3.0 liters is equal to 4.0 molar. So 4 is the molarity on SO3. We didn't have any of the products, so those are just 0 molarity. Then we're ready to do the change row. So again, that's where we use those coefficients again. This reaction, we think about where it's going to go. We started with all reactants, so it's going to have to go right towards products. Because it's going right, we're going to expect to use plus x over there on the products for SO2 plus 2x, again, because of the coefficient there. For SO3, again, it's a reactant, so it's going to be used up, and it has a coefficient of 2 as well, so minus 2x there. Then I just always add I plus C to get equilibrium, so 4 minus 2x, and not 2x, but just x. Now I'm at that last point of using the table to determine x, k, any of the unknown concentrations. So let's look at the other information we were given. At equilibrium, there's 3 moles of SO2 present. Since the volume of the container is 3 liters, that tells me that SO2 at equilibrium is 3.0 moles divided by 3.0 liters is equal to 1.0 molar. Again, I can also relate that to my table, so that 1 molar for SO2 at equilibrium is also equal to 2x from my table. And then I can, from that, divide both sides by 2 to solve for x is equal to 0.5. Okay, with that out of the way, now that I know x, everything else is a lot easier because x is 0.5, so I know the concentration of O2 at equilibrium is 0.5. SO2, the calculation was 1.0. For SO3, it was 4 minus 2x, so 4 minus 2 times 0.5 will give me an equilibrium concentration of 3. So this is going to be 3.0 molar, just doing that same equilibrium row, but in molarity. This is going to be 1.0 molar, and this is going to be 0.5 molar. With that done, now I can plug into K equals Q. So at equilibrium, K is equal to Q. So therefore, K is going to be equal to, my Q at equilibrium is SO2 squared. So SO2 squared, SO2 was 1.0, so 1.0 squared times, if I look at the rest of my numerator, O2 to the first power, so 0.5, divided by, in the denominator, I have 3.0 squared. So that's my overall expression for K. Plug in and solve. And when I do that, I get 0.0, let's see, 55. If I round to 2 sig figs, 0.056 is equal to K. So in this case, this reaction is relatively reactant favored. We can see that based on the equilibrium concentrations as well. We have a little bit of products, 1 molar and 0.5 molar, but most of our reactants just stayed put as reactants. We started with 4 molar reactants, ended with 3 molar reactants, and so K is in this case sort of a little bit or slightly less than 1. It's a slightly reactant favored type of reaction. So these problems really give you a good handle on just the nuts and bolts of building and using ice tables. Again, we've talked about this when evaluating each of our answers to the previous 2 problems, but important to keep in mind that the value of K, which is again sort of where you'll end up with at equilibrium, will tell you about whether your reaction favors reactants, favors products, or is somewhere in the middle. So again, if K is really small, we're over here, mainly favoring reactants. I've got the nice color coding, reactants are purple, so mainly reactants when K is small. Mainly products when K is large. Again, we can see that just on our number line as well. Since our number line runs on the left at reactants, all reactants at 0. On the right, all products, it's infinity. So it all does sort of match nicely. In the middle here with intermediate amounts, we're going to have similar amounts of reactants and products, which is sort of where we were for that second example where it was about 0.056, so somewhere in this intermediate region, somewhat similar amounts of both reactants and products. That's going to be important when we choose what method we're going to use to solve future equilibrium problems. If the reaction really favors reactants strongly, we'll be able to make additional approximations that will make the math a lot easier. Okay, so next we're going to build in these next steps that go through how to solve for the equilibrium concentration. So we'll go through these in turn, but these are the 5 sort of methods that we could use to solve for equilibrium concentrations. Based on that last slide, if the reaction lies towards reactants and K is small, which is sort of a K less than 10 to the minus third is a pretty good idea, we're going to be able to make this approximation. Otherwise, we have these methods to solve exactly. And again, we also have this sort of 5th option, which is going to be successive approximations, which again, you could use solver there as well. So again, these will go through one at a time, doing some example problems to show how these methods work to solve for the equilibrium concentrations. Okay, so here are our general steps for solving each equilibrium problem. We've looked at that first step. First, write the balanced chemical equation, the equilibrium expression. Then we fill out our ice table. We should look at the value of Q initially to figure out the sign of X. So we'll show doing that as well. Next, once we are doing this type of problem, we're usually going to be given the value of K. So if we're given the value of K, then we're going to choose the appropriate method to solve from that list on the previous slide. We'll solve, go back into our ice table and check our answer. So these are all the steps, but let's see what those look like one. So here's our first example problem that we're going to do. We're given some concentrations of PCl₃ and Cl2 that combine to produce PCl₅. We're given the value of Kc, and now we need to go through and calculate what the concentrations of each of these substances are at equilibrium. Okay, the first 2 steps are just the same that we've been doing. Again, try to do these on your own. You can pause the video and then come back and take a look to see if you've gotten it right. Okay, so we're given PCl₃ and Cl2 to combine to form PCl₅. If we look at this, it's already balanced as is, so there's no additional coefficients that we need. All the coefficients are going to be 1. K equals Q, I forgot to write that down, but I'll write that down maybe over here. So the reaction quotient here is PCl₅ over PCl₃ times Cl2. That's equal to Q, and then at equilibrium, that's also equal to K. So this whole thing is also equal to my K, which is a number 1.60. Now I can fill out my ice table. In this case, we didn't have any unit conversions to do. We're given the proper units. Remember, molar or moles per liter is going to be the right unit generally to use on our ice table. So we can just plug directly in 0.200, 0.100. Now the change row, just like the previous examples, we started with all reactants. The reaction is going to have to proceed right towards products. So we'll use plus x of the product. The coefficient is 1, so just plus 1x minus 1x of each reactant because the coefficients are both 1. Then at equilibrium, I get 0.2 minus x, 0.1 minus x, and x. That's something we've done on the previous examples. Now we're at the point of choosing the method to solve. The idea there is that's going to depend on the value of x at the value of k at equilibrium. So if k is less than about 10 to the minus third, approximating is going to normally be a good way to do this. That doesn't apply here. K is not very small. K is 1.6, so we expect to see roughly similar amounts of reactants and products. So we're going to need to solve exactly here because K is a lot bigger than that, 10 to the minus 3. For solving exactly, you've got 3 choices that will generally work. One is sometimes there's like an algebra trick. Like you can just take the square root of both sides or something like that. Number 2 is going to be the quadratic equation. And number 3 is going to be solver on your calculator. So we'll show, in this case, what we'll see is that there's no trick that will get the answer, but we'll show both quadratic and solver. You can sort of choose which of those you think is a better approach going forward. Okay, so now that we have our k equals q in our ice table, we now have this down to just sort of a math problem. So we plug into that k equals q. 1.6 is equal to, looking at the equilibrium row, PCl₅ is x. So up on the top here we have x divided by PCl₃ is 0.2 minus x. And Cl2 is 0.1 minus x. So that's our overall equation. 1.6 is equal to x over 0.2 minus x times 0.1 minus x. There's no simple algebra trick that will get us to the answer. So maybe let's first try the quadratic equation. For this, you'll always be given the quadratic formula. But just as a refresher, the quadratic formula, which you'll be given, is if you write the equation in the form ax squared plus bx plus c is equal to 0, where a, b, and c are your coefficients, some numbers, then these two solutions that you get out are negative b over 2a plus or minus b squared minus 4ac divided by 2a. So this approach, we have to basically make this equation, rearrange all the variables to get it into this ax squared plus bx plus c is equal to 0 form. So the steps of algebra that we need to do there, we're going to need to get everything out of the denominator first. We can't have a denominator in this sort of approach. So we've got all this stuff in the denominator, so we're going to multiply top and bottom, or in this case, multiply both sides by all that stuff that's currently in the denominator. So 1.6 times 0.2 minus x times 0.1 minus x is equal to x, 0.2 minus x, 0.1 minus x, and then again I'm multiplying that on both sides so that I can get it out of the denominator. So that was the goal. That canceled all of this stuff and just leaves me x on the right hand side. Again, there's some different terms there, but you know, ends up just sort of being moving all this stuff over to the left hand side. Now I'm at the point where I could start doing the algebra. So this is another sort of math case here. FOIL is, I don't know the acronym I know for this. So FOIL is first, outer, inner, last, for just keeping track of all the terms you need in this multiplication to expand that. So 1.6, then the different terms here, I've got first is this term, so first term in each side, 0.2 times 0.1 is 0.02, minus, if I do the next one, I've got outer, so minus, this is 0.2 times x, so that's just 0.2 times minus x, so minus 0.2x, minus the next term is minus inner, x, negative x times 0.1, so minus 0.1x. Then the last term is last. Negative x times negative x is plus x squared, since negative 1 times negative 1 is positive 1. Now I can multiply. I could actually divide 1.6 by both sides, but I'll just multiply both sides. This through on all the terms here. These two terms I can combine. So I've got 1.6 times 0.02 minus 1.6 times 0. Oh boy, that x is bad. I'm going to get rid of that x. 1.6 0.02 minus 1.6 0.3x plus 1.6 x squared is equal to x. Multiplying those out, I get this. I've got x still on the right-hand side. I always need to get it into 0 on the right-hand side, so subtract x from both sides. I'll do that, and I'm also then just going to rearrange this into the form that's convenient for ax squared plus bx plus c. So I'll write it then as 1.6x squared. I had a minus 0.48, and this is 1x, so minus 1.48x, and then plus 0.032. I didn't have to do that, but that way it's in sort of the normal format. That then tells me that my coefficient of A is equal to 1.6, my coefficient of B is negative 1.48, don't forget the negatives, and my coefficient of C is equal to 0.032. Just lining these up with my A, x squared plus bx plus c is equal to 0 equation. Now at this point I can plug into the quadratic formula and get my two values. Okay, so I've showed plugging all of this in, negative b over 2a. Since b had a negative, negative times a negative is positive 1.48. Really check your signs very carefully here. That gives me 0.4625 for that first part of this equation. Then in here, negative 1.48 squared. So this, again, it's not negative 1.48 squared, it's negative 1.48 squared, which makes this a positive number here. Be careful with your signs. You do have to type it in with the parentheses around the negative 1.48, or just ignore the negative here because it'll be, a positive number. Minus 4 times 1.6 times 0.032. Again, here, however, if you look, the negative signs are going to be really important. So they're both positive, so minus 4 times 1.6 times 0.032. If you do all that math right, you should get the top is going to be square root of 1.9856 divided by 0.32. That gave me, for this part, I didn't write that out, this term here simplified to 0.4403 was what that whole term here simplified to. I would not do this. I'll show you in a second. That unless you only have like the most basic graphing calculator or the most basic scientific calculator, the other types of calculators can, once you solve for a, b, and c, they have the quadratic formula built in. So you just type in a, b, and c, and it will calculate these two known values for you. That can save you a little bit of time. I'll show you that in a second here. If you have a TI-36, once you get it to this point here, you can just type it into your calculator. So you go second, this cosine key to go to polynomial solver. This is just the quadratic, so number 1. Then it'll give you this entry where you type, the A coefficient 1.6, enter, go to the B coefficient negative 1.48. the C coefficient, type that in, then go and hit solve. And then it'll give you x1. If you scroll down with the number pad, you can get to x2, and those values are stored there for you. If you go all the way down at the very end, you can actually store one of those values to one of your functions. So one more click down will take you to a place where you can like store x2 to the value x, and then it'll be there for you if you want to get that value out. In any event, either method you use to solve for x, you now have two possible values of x, 0.903 or 0.022. Now we need to check our answer, or really in this case just choose the correct value of x. So Quadratic gives you two solutions, but one of those is never going to be physically meaningful. So the way we can check that is always by looking for the solution where all the concentrations are positive. So in this case, let's check to see if 0.903 will work. If I think about PCl₃ at equilibrium, that's going to be 0.2 minus x. But if x is 0.903, I'm going to get negative 0.20 molar, which is not possible. And therefore, because we got that negative concentration, which is impossible, concentrations have to be positive, we know that the correct value of x has to be this one, 0.022. Then I can go in and, again, sometimes once people get the value of x, they want to just stop. They think they're done, and you have done a lot of work. But we now need to get the final part of this, actually answer the question, what are all the equilibrium concentrations? So in this case, just plug in the correct value of x into the equilibrium row. So grabbing all of these values to three significant figures, which is what we're given in the problem, 0.178 molar, 0.0778 molar, and 0.022 molar. At this point, again, on a quiz or exam, I definitely recommend to check your answer even further. A good approach there is to just plug back into the K equals Q expression. So this final check, PCl₅ is 0.022 divided by 0.178 times 0.0778. Again, if you don't want to use this division type calculator operation, remember to put parentheses around that whole denominator. In that case, you should get something like so I get, when I do this, I get Q is equal to 1.603, which is a good match. Again, my K was 1.60. So when I did this, I did actually get Q equal to K, and that verifies that I have the correct solution. So really all of this part of exam 3, a huge chunk of it is just applying this approach correctly, checking your answers, making sure to have proper units, just doing that for all sorts of different types of problems. Here's that same solution in sort of the PowerPoint format. So going through, again, once you fill out your ICE table, you need to pick the correct method to solve. Because K is close to 1, we're not going to be able to approximate. We'll introduce that method in a minute. So we showed the quadratic formula here. It's one good approach, A, B, and C, and just these same slides plugging in. Note, however, another good approach here is once we got to this point here, we've actually done all the chemistry. Once we've set our K equal Q and got all of this in here. So the alternate approach on the graphing calculator or TI-36X is to plug into the numerical solver. So that's a great way to do this. If I use the TI-84, I can get that via math, and then I go all the way down here to B to choose solver. On some versions of TI-84, it's 0 equals, so you have to force everything equal to 0. A lot of other versions of this calculator, you don't have to. It lets you choose the two sides of the equation independently, in which case you can just type 1.6 on one side and do x divided by the 0.2 minus x times 0.1 minus x on the other side, just depending on how your calculator works. again, the Ti-836X can also do this just as well. So in this case, again, if you have these two things in the denominator, you need these parentheses on both sides to force all that stuff into the denominator. So it is a little bit unwieldy with those parentheses. Again, the other approach is to use that sort of division operator, which you can get on the Ti-84 from the, so that's another approach to force it into look like a nice fraction. At that point, then you press enter, and you always have to choose a guess if you're going to use this. So the way this works is based off this initial guess. X equals 0 is usually a good guess, but sometimes your X will be some random number from a previous trial, so you can always just type 0 again. The bounds here default to, this huge range of bounds, usually fine. Then you press alpha enter to solve, so you have to do that. When you're on the 0 key, then use alpha and then enter to solve. It will then chug along for a few seconds and give you the solution. In this case, it picked the 0.022 solution. That is the correct one since all concentrations are positive, but let's say you picked a different guess so that X came out to be that 0.90 solution. You still need to go back and say, hey, this actually doesn't make sense because the concentrations are negative. Let me try a guess of, say, 0, or again, maybe if a guess of 0 doesn't work, you could try negative 0.1 or something like that. Usually that won't be what you need. Usually a guess of 0 will work pretty well. But yeah, you definitely are responsible for checking your answer and making sure everything looks appropriate. Again, this does save quite a bit of time on the algebra potentially, so it can be a good way to solve these problems. Here's our next example, so try doing those first couple steps on your own, and then I'll show you how we can introduce that approximate method to solve. Okay, those first few steps, the balanced chemical equation is given. Okay, so in this case, 7.1 times 10 to the negative 4 over here is equal to H3O plus times F minus over HF. Remember, H2O is a pure liquid, so it doesn't show up in the equilibrium constant expression. Its concentration is always constant. That means that when we write out our ice table, it's perfectly fair to say that H2O, while it does change, it is going to have sort of a minus X moles of H2O. Since its concentration is going to stay basically constant, then we don't need to worry about it since it doesn't show up in the equilibrium constant expression. Even though it is being produced and consumed in the reaction, it's not going to matter for our ice table or for our equilibrium constant expression, so we can leave it out. HF, the initial here, is 0.500. The change, these start at 0, so we're in that common situation where we start with no products, and so the reaction is going to have to go to the right, so we'll form plus X of each product. All the coefficients are 1, so we don't have any of those to worry about. And then HF is our reactant, so it's going to get a minus X. Again, coefficient of 1, so just minus X. Equilibrium then, 0.5 minus X, X, and X. Now we're all ready to go and get started trying to solve this problem. We may as well now plug into K equals Q. That's always sort of our next step here. So I'll do that over here. 7.1 times 10 to the minus 4 is equal to H3O plus is X, F minus is X, divided by 0.5 minus X. So that's just plugging in here. H3O plus was X. F minus at equilibrium is X, and then plugging in for HF, 0.5 minus X. Now we need to choose a method to solve the equation. So in this case, K is in fact less than 10 to the minus 3. And so our assumption here is that this equilibrium is going to apply pretty far to the left. There's only going to be a small amount of products formed. Therefore, what we're going to do is make this small x approximation. So the small x approximation, the idea behind that is that we're going to have 0 anytime we take a big number minus a small number here. So 0.5 minus x is just going to approximately be 0.5. That's what the small x approximation is. Since x maybe is going to be like 0.0001 or something like that, when I take 0.5 and subtract off such a small number, it's still going to be approximately 0.5. So that's the idea, is that we'll be able to say that this is approximately equal to x squared as the top over 0.5. And that's always the approximation that we're going to make. If x is in fact small, because again k is small and equilibrium lies to the left, then it makes sense that this, of the 0.5 that I started with, I'm still going to have very close to 0.5 molar HF at the end. Now, what's so great about this approximation is instead of needing to do quadratic equation or go into solver or anything like that, now I can just sort of solve this with a square root. If I look, I just have x squared on the right. And so if I want to solve for x here, I can just multiply both sides by 0.5. So 0.5 times 7.1 times 10 to the minus 4 is equal to x squared. Again, I'm going to drop the approximation sign for now. Now, again, that was multiplying both sides by 0.5, which, moved canceled the 0.5 over there. Now, to solve for x, I just take the square root of both sides. So I've got that then gives me a value of x, which is, I get 0.0188 molar here. Now, technically, I'd also have a value when I take the square root here. I do actually technically get plus or minus over here on the left-hand side. In this case, though, I know x has to be positive because I started with 0 of the product, so I don't really have to worry about the negative solution there. So even though this isn't 100% right from a math perspective, yeah, we are going to have just the positive value of x is the correct one here. Now I need to go back in and plug back into the ICE table and check my answer. So in this case, for approximations here, I'm going to need to make sure that that approximation was valid. So in this case, we use the 5% rule to judge the validity of that approximation. So we're going to say, is x less than 5% of 0.50 molar? We assumed that x was small, and so 0.5 at minus x was about 0.5, and our judgment of how small x is that it does need to be about less than 5% of that value. So we can do that comparison. 5% of 0.05 is 0.05 times 0.5, which is 0.025 molar. 5%, right, of means times. 5% is 0.05, so our judgment here, is x less than 0.025 molar? Yes, it is. It's not much less, but it's a little bit less than that. And therefore, that was a sign that x is in fact pretty small. And our approximation should be valid. So we've checked our answer. We've solved for x. We do need to plug back into the ICE table to get whatever values we need. In this case, the thing it's asking for was the concentration of H3O+. And so the concentration of H3O+ is equal to x is equal to 0.0188 molar. I only have 2 sig figs on K, so I can round that properly to 0.019 molar. So this check shows us that our Q is 7.4 times 10 to the minus 4. Pretty close. Again, we did make this approximation. We're not exactly at 7.1 times 10 to the minus 4, but close enough. And that's just another check that everything has been done properly. We can see here as well that H3O+ and F- are 0.019. So we have a relatively small amount of products compared to our reactants, which is still close to 0.5. So since K is less than 1, and in this case significantly less than 1, we have mainly reactants and only a little bit of products formed. So all those things show that this is a reasonable solution. And this approximation method is always the method I would use if it's a valid choice. If K is small, this is very fast, not a lot of chances to make mathematical errors, and it works really, really well. Just as before, this is just showing those steps in case, my by hand math was a little bit confusing to follow. Just that same steps in the. Again, 5% approximation, you should always be prepared to make that check, because if it's not valid, you have to choose another method to solve instead. Our next example, you can take a minute to try this. So this one, I would say try to do, pretty much the whole problem. Try to do all the steps. In this case, it says to approximate, and then go through and check, okay, does the approximation method work? So take a few minutes to try to solve that. And what you should find is the approximation method doesn't work. You're above 5%. So what we'll spend time on is looking at, okay, what happens if the approximation fails? What can we do to fix it? Okay, the first couple steps here, writing out the K equals Q. Since H2O is a pure liquid, it doesn't show up there. I don't know what I did here. That's all backwards, so H3O plus NO2 minus over HNO2. Sorry about that. Products over reactants. Then the ice table here, 0.1 molar HNO2, so that goes there, minus X plus X plus X. We start with 0 of the product, so we have to have this reaction proceed right towards products. Our equilibrium row, initial plus change, 0.1 minus X, X and X. In this case, we think that approximating should work well. K is pretty small, so we should try our approximation method. Okay, so in this case, our approximation method would say we expect X to be pretty small compared to 0.1, so we can get rid of that minus X term down there. Again, that's the approximation that we're making. We're basically saying X is close to 0. Then multiply both sides by 0.1 as usual, and we get this. 5.6 times 10 to the minus 4 times 0.1 is X squared. Take the square root of both sides, and we get X is equal to, so 0.00748 molar. Now I do my check. We wanted it to be, we are going to say X is less than 5% of 0.10 molar, because that's the approximation we made. We neglected the minus X right there. 5% of 0.1, I can move the decimal place. 0.01 is 10%, divide by 2, so 0.005 molar is 5% of 0.1. Is X less than that? No, X is in fact a little bit bigger. It's 0.00748. That's not less than 0.005. The approximation wasn't valid. In this case, one easy way to fix this is to apply successive approximations. So successive approximation says that what we can do is, our initial guess was that X was 0. That's what we assumed. Since X is small, it's going to be pretty close to 0. But now we actually have a better guess for the value of X. This initial procedure we did said, well, actually X should maybe be pretty close to 0.00748. So what we do is we label this our first guess for X. Now we go back, and instead of ignoring the minus X, we keep updating our guess. So what this is going to be then is, it's the same equation, square root of 5.6 times 10 to the minus 4, but the term that's going to change is that second one here. So this one here was previously just 0.1 because we assumed X was equal to 0. Now I'm going to do 0.1 minus X1 is my new guess. So I'm going to say, well, now X is probably pretty close to 0.00748. So that's the math I'm going to do. 0.1 minus 0.00748 is my answer, and I'm going to let that equal to my next guess, x2. This works pretty quickly on your calculator. You can just sort of go back to the previous thing and do your square root again. So square root 5.6 e minus 4 times 0.1 minus 0.00748. Again, just adding all the sort of parentheses that I need. Let's see, what did I do wrong there? Oh, 0.00748. And when I do that, I get my new value of x2 is equal to 0.00720. That's pretty close. The point of a successive approximations is I just do that exact same procedure again. So I'm going to do square root of 5.6 times 10 to the minus 4 times, now my guess is 0.1 minus x2 is my new guess. And this one should end up staying pretty consistent. So I just go back, click that up arrow on my calculator, and I'm going to replace 0.00748 with 0.00720. I don't have to retype that whole thing, right? If I just click that up arrow to go grab a previous calculation, I can just edit that value. And when I do that, I get 0.00720 again. And that's a sign that now I do have sort of a self-consistent answer, since I got the exact, oh, 0.00721, sorry. But it's close enough. Remember, I only have 2 significant figures here. And so we are good. This is not changing by enough to be important anymore. And this is now my best guess for x, is my initial approximation was slightly off, but 0.00720 or 0.00721 is going to be a better guess. At this point, I can go in and do all the rest of the problem. If I want to know the concentration of H3O+, that's just equal to x is equal to 0.007 to 2 sig figs, 0.72. That's the exact same as the concentration of NO2-, because those are both equal to x in the ICE table. My concentration of HF, if I need that, is equal to 0.1 minus that 0.0072 is 0.09. Let's see, 27.0928. I guess 0.093 to 2 sig figs there. So this is a little bit more work, and you're certainly free to also, if you find the approximation fails, you're free to go back and use the quadratic or solver at that point too. That would be another good approach. But successive approximations is a pretty fast way to just sort of keep making that same approximation, but update your guess, and keep plugging that in. This just shows what that looks like on a calculator. If you use that store function to store the value to a variable x, this is really convenient. So 0.00748, my initial guess, I store it to x. Then I do square root, just type this formula in. With the x in it, I get my new value. Now, again, since I still need to do another one here, since this didn't stay the same, I go in and I, select this thing, then click store x, enter to update my stored value. Then I just, use the up area to grab this value from sort of 2 lines up on the calculator, pull it down here, click enter again, and I get my new value. So, not actually too much additional typing here. It's really only a few extra lines once I got to realized I needed to do successive approximations. This is just those same steps shown sort of mathematically here. X, the new value of x is equal to sort of the old value of x according to this equation. Our initial guess for x is 0, so that gets us x1. Then our new guess is x2. our third guess is x3. I think we're done here because we only have two sig figs in the final answer, but you could do it one more time and get the same value to 3 sig figs, which is the same value that you'd get if you actually use the quadratic formula or use solver right away. Now, again, it's actually pretty fast to plug this into solver, so it wouldn't be a terrible idea here to just go right to solver. So that's always another option. See that this doesn't work, go back in, type this into your numerical solver, choose 0 as your guess, choose solve, and you get x equals 0.00721 or 0.00728 out of numerical solver as well. Whatever you're most comfortable with, quadratic, solver, successive approximations, lots of reasonable choices here. I would always encourage you to just use the normal approximation when you can, when it works, because that is just so much less typing and so much less work than anything else. So again, trial 2, it's another way to do this is as long as you're within that sort of 5% or again, to 2 significant figures have the same value, it would be fine to stop here after that next trial. So usually not the greatest source of error. There are lots of other things that limit our knowledge of K's to within about 10 to 20% normally. We've now introduced all the key types of methods that will let you solve equilibrium problems. So this is just another example. Solve using whatever method you want, and I'll show the solution here later. Again, if you're having trouble with the math aspect, please contact me via email or stop by office hours. This same procedure we're going to keep applying over and over on exam 3. So if you can figure this out and have a strong grasp of it, you'll do well on exam 3. Okay, so I'll write out the steps here. We're given the balanced equation, so we can proceed right to K equals Q. The Q here is NH4 plus OH minus over NH3, which is equal to our K of 1.8 times 10 to the minus 5. Then for our ice table, this is that common case where we have water, which we can ignore because it has a constant concentration. We start with none of the products, and we start in this case with 0.05 molar of the initial reactant. Because we start with no products, we're going to make some amount of each of those. So these are going to each get to be plus x. Coefficients are all 1, so that matches. The coefficient on NH3 is 1, and it's a reactant, so minus x there. Consuming some reactants, making a little bit of products. At equilibrium, xx and 0.05 minus x. Now choosing the method. In this case, quadratic or solver or approximation would work because K is quite small, so we expect small x approximation should work. In that case, when we plug into K equals Q, we get this sort of expression, and the small x approximation will say, okay, well, since x should be small, 0.05 minus x is probably going to be about equal to 0.05. So that's the approximation we're going to make. Now it's that same relatively simple math situation where we can multiply 0.05 times both sides. That is equal to x squared. Take our square root, and we get x is equal to 9.49 times 10 to the minus 4 molar. So checking our approximation, the 5% rule would say, okay, we hope that x is less than 5% of the thing we said it was smaller than. We said x was a lot smaller than 0.05, so less than 5% of 0.05, that's again 0.05 times 0.05, which is 0.0025. Is x less than that? Yes. 0.0025 is 2.5 times 10 to the minus 3, and x is definitely less than that. It's, 0.95 times 10 to the minus 3, so about a factor of about 40% as big as this number. So yes, this approximation does work. All our concentrations should be positive. That should work out here because we've got 0.05 minus x. That's definitely positive since x is so small, and each of our x's are 9.5 times 10 to the negative 4. So now we're ready to give our final answer. Again, in this case, it wants all the concentrations, so we plug into the ice table to get all of those. We have NH3, NH4 plus. So that, again, plugging into the ice row, 0.05 minus this x is 0.049. NH4 plus is 9.5 times 10 to the minus 4. OH minus 9.5 times 10 to the minus 4, since those were just equal to x. And again, if we wanted to do one final check, we could plug into the K equals Q one final time to verify that we do, in fact, have the correct final concentrations. When I do that, I get Q is 1.83 times 10 to the minus 5, which does, in fact, match. So this solution works, and we have the equilibrium concentrations. Okay, here's one final example. You can try to do this one yourself. I'll tell you that this is a case where if you pay attention, there is an algebra trick here. So even though you could use some of your other methods like quadratic or solver, in this case, if you look at the form of the K equals Q expression, there is an algebra trick that you could apply as well. Okay, so when you solve this one, the equilibrium expression, products over reactants, looks like this. Setting up the ice table, we start with just the reactant, 0.025 minus 2x, 0, 0, plus x. Then if we think about what method we want to use, this sort of guessing the solution step, K is less than 1, but it's not much less than 1. So probably approximating isn't going to work. And so we are going to need to solve exactly. So that's the idea. Again, it's greater than 10 to the minus 3, so that isn't going to work. In this case, though, when we actually plug in, so okay, we're going to need to solve exactly, so any of our exact solution methods could work here. When I plug in, I get something like 0.022 is equal to the products are x times x over the reactants are 0.025 minus 2x, the whole quantity squared. Sometimes people will forget their squareds here, so if you write out K equals Q, you got that squared there. Definitely remember that when you go back and plug in. And so this gives us 0.022 is equal to x squared over 0.025 minus 2x, the whole quantity squared. So this is the case where we actually have a perfect square on this right-hand side. So since it's a squared on the top and on the bottom, this is this case where we can just use our algebra trick. And even though it's not the case where we can like approximate and make a square root, actually the exact solution, we can take a square root of both sides either way. Now, again, you don't have to use that method if you like doing the quadratic, or especially in this case, solver would work, very easily. Those methods work just fine as well, but this exact algebra solution does. What do we do there? Take the square root of both sides. That gets us 0.148 on the left-hand side and x over 0.025 minus 2x. Now, technically, this 0.148 is not exactly correct because when you take a square root, technically you have the plus or minus, right? If I said 4 is equal to x squared, the valid solutions here are x is equal to plus or minus 2. So technically, when you take the square root, we can't assume that it's just the positive one. In this case, though, that's okay because we know that x has to be positive based on our ice table. So if you look back at our ice table, since we start with none of the products, x does have to be positive, and so this is going to be the correct root. Then do some algebra here, multiply both sides by 0.025 minus 2x. Simplify, do the steps of algebra, and you get 0.0029 molar is equal to x. Don't round too early. That can cause some numerical issues. In that case, though, we do get a value of x and can then get the final answer here. So now that we have a value of x, we can plug back in. 0.019 is HI, H2 is 0.0029, I2 is 0.0029. All the concentrations are positive, which is always has to be true. We expect the product concentrations are going to be a little bit smaller, so these are a little bit less than the HI because K is less than 1, so that checks out as well. And is Q equal to K? Again, just plugging in, yeah, it does end up being basically correct to within a little bit of rounding error, so those all check that this was a valid approach. So this procedure is really the key information from this set of notes. If you have trouble with any of these steps, calculator issues, please stop by or send you can take pictures of the calculator or your work, send it to me. Definitely don't wait to get help once you start trying these problems, so that you have this procedure really well in hand by the time you get to the quiz and the exam.